Thank you. It's a pleasure to be here. I think I have the most fun job at NVIDIA because I get to sort of play with new technology, figure out what's going to go into GPUs in the future. The organization I run is called NVIDIA Research. It's roughly 500 people, and it's loosely organized into a supply side and a demand side. The supply side develops the technology that makes GPUs better, from circuits to the architecture to the programming systems. The demand side drives demand for GPUs. It's where we did the first work with AI, autonomous vehicles, quantum computing, and basically builds applications so that there's a huge demand for the products that we make. Occasionally, we pull a bunch of people from different groups together and do an integration moonshot. We did one of those a number of years ago that developed what we called the tree traversal unit, and the marketing people thought a better name was the RTX core. We basically made ray tracing real time. We're doing another one right now on very fast inference, and I'm going to tell you a little bit about that shortly. And occasionally, we'll pull people together to study a topic. We had a quantum study group that led us to form our strategy for quantum computing, deciding to work on simulation tools leading to the development of cuQuantum rather than try to build quantum computers ourselves. Over the years, we've had a fair amount of impact on the company. I like to think of this as our greatest hits slide. Probably the biggest hit is on the right side of the slide, is we got NVIDIA into AI. I had a colleague, Andrew Ng at Stanford, who was working with Google finding cats on the internet. And I assigned an NVIDIA researcher, Brian Catanzaro, to work with him and port that software, instead of running on 16,000 CPUs, to run on 12 GPUs. And the result of that became CUDA and really launched NVIDIA down the path of being the leader for hardware for AI. We got NVIDIA into networking. While we were building supercomputers for the Department of Energy, I negotiated a research contract to develop networking for GPUs, NVSwitch and NVLink. What's interesting is at the time, the Department of Energy wanted a 40% cost share. They wanted to pay 60%, we would pay 40%. It seemed like a great deal to me. I went to Jensen, and Jensen said, no, I'm not gonna pay 40% for networking. We don't do networking, we do the compute, somebody else does the networking. And so I had to go back to the DOE. Fortunately, they agreed to pay 100% of it, and before we were done with the research project developing the first NVLink and switch, it kind of pulled out of our hands, and the first links got put into Pascal in the first NVSwitch, which actually started as a research project, wound up being the switch in Volta. And then all of ray tracing at NVIDIA came out of NVIDIA Research. We started developing a piece of software that we demoed at SIGGRAPH in 2009 and 2010 that became optics, the core of our professional graphics offering. And then a few years later, in 2013, we had this crazy idea that by building some hardware, we could make ray tracing 100 times faster and make it go from being about 1 frame per second, which is what optics was, doing really high quality rendering for architects and automotive designers and people like that, to making it be 60 or 120 frames per second, good enough for real-time graphics. And the result of that research project became what we called the tree traversal unit, because it traversed a bounding volume hierarchy, the key data structure in ray tracing. Marketing people thought that RTX cores sounded better, and so that was the origin of the RTX cores and ray tracing for professional graphics, or for real-time graphics. And it's really changed the nature of games and made photorealistic rendering in games much better. There are a bunch of other things we've done. I don't have time to go into it all. I've been doing these presentations now since 21, so there have been 6 of them, and they've always given me an hour, and so I covered 4 things, and these are the things I've covered in the past. I'm not going to go through them. This year they only gave me 40 minutes, so I originally had 4 things. I rehearsed the talk and it wasn't going to fit, so I had to cut out the how we're using AI to design hardware, which was actually pretty cool, but it didn't fit. So these are the things I'm going to talk about today. How we're making inference more efficient. What are the things that drive that? How we overcome the data shortage by using reinforcement learning during pre-training to get more value, more accuracy in a model out of the same amount of data. And then I'm going to talk a little bit about what we're doing with robotics with our Groot robot models. So let me start with efficient inference. Jensen showed a slide that looked a little bit like this during his keynote. I downloaded this just a couple days ago on March 13th. This is from Semi-Analysis with their Inference X benchmark, and it really shows what you care about for inference. And depending on your application, if you don't care about real time, if you're running a batch job, you're going to come back tomorrow, look at the results, you want to be way over on the left side of this chart, because that's where you get the most tokens per second per GPU, essentially tokens per second per dollar, tokens per second per watt, by grouping things together into large batches. And that allows you to then amortize fetching a weight over the entire cost of that batch, and you have less demand on memory bandwidth, less energy burn fetching those weights, same amount of math, but done in a more efficient way. But if you ask an LLM for an answer and you need it right now. For example, this might be the LLM that we use in our Alpamayo self-driving car software. That actually is a transformer. It's actually not a large language model, but it's a vision language action model. You still need very fast response. It's a real-time system, and so you need it to respond at perhaps 100 tokens per second. But if you're going to be reasoning, you actually need it to respond faster than that, because to get, say, 100 tokens per second to you, it may generate 1,000 tokens. And so now you need 1,000 tokens per second. And you may be doing tree of thought. You may be doing other things that consume, in an agentic system, a lot more tokens. So there are reasons, if you're interacting with people or in a real-time system, you want to be over on the far right-hand side of this chart, where it's basically interactivity that you're paying for. And this chart only goes out to 350. Some of the stuff I'm about to tell you about, we feel can get us out to order of 10,000 tokens per second per user, so for a single flow. This is really what the demand is. The model sizes are growing every year. We're basically doing 5 times as many tokens per year by doing this thinking that's going on in the middle. And to meet this demand economically, we have to continue to reduce the token cost. So here's sort of a cartoon of that chart I just showed you. The previous one was real data from real GPUs. This one is a little bit more of a cartoon. And so if you're worried about tokens per second over on the right side here, 2 things drive that. The first is bandwidth out of memory. So every time you go through the transformer, when you're in the decode phase of inference, you basically have 1 token, but that token has to see every weight in the model, or at least every weight in the experts that are selected for that token in the model. So you're very much limited by the memory bandwidth to read all those weights out. Every time you read one of those weights out, you multiply it once by that 1 token, unless you're able to batch up a little bit. And actually, as you go up the curve, it's largely by increasing batching as you move to the left side here. The other thing that matters a lot is communication, because after you've done that 1 multiply, you now have to move the result of that and position it for the next stage. Typically have maybe 5 matrix multiplies per layer, 80 layers, order of 500 stages to get from 1 token to the next token in inference. And there's a communication action that happens there, both on chip and off chip. At the other end of this chart, where you're really worried about throughput, it's really about being very economical with data movement, because that's what's going to burn the energy in this. You have to do the same amount of math anyway, but you'd like to do as little data movement per unit of math as possible. I think I said all of that. This is a breakdown for an accelerator that we've prototyped in NVIDIA Research of where the time goes for the latency limited decode part on the right side of the chart, and where the energy goes for the energy limited part on the throughput side of the chart. And what you see is that latency is all communication. The compute and memory time is that little 11% wedge. The communication time is roughly evenly divided between the on-chip communication in purple and the off-chip communication in a lighter purple. Better colors here. On the power side, what we see is that weight and data movement, account for the bulk of this, and compute counts for 59% of this, and then weight and data movement. In a conventional GPU today, the chart looks more like this one, where 73% is the weight and data movement, and the compute is only really 9%. And it's by organizing the computation to eliminate data movement that we wind up being able to do much better than that. So let me talk a little bit about how we do this. The first thing to realize is that the best way to eliminate data movement is to put the math right at the edges of the SRAM where we're reading the weights or KB cache entries from. So by building a unit which has a bunch of SRAM and then a bunch of math units, we can basically eliminate data movement. We read the weights, we have the activations available in that blue register there, we do the multiplies right there, and with no data movement we produce the output activations. We then can basically tile this, covering the majority of the die in these things that we're calling PEs here, and then have a reticle-sized die full of these. And after every stage, where we basically do a matrix multiply by doing 1 row at a time, by reading weights, doing a multiply by the essentially a dot product by the activations, that produces a single output activation. We then can collect those output activations, do an on-chip communication, and prepare for the next stage. After a few of these, we need to move to a different chip, and that's an off-chip communication. So chip group 1 will do, say, attention block 1. Chip group 2 will be the mixture experts. We'll then do attention block 2 and so on. And when you look at where the time goes in this, it's basically spent communicating, both on chip, basically taking these activations that we get out of doing the dot product in each of these PEs and shuffling them around to be the input activations for the next stage. Or then between stages, it's off-chip communication where we have to send a message from one of these chips to the next chip to start the next layer. So what sets this upper bound here is communication latency. And so what we'd really like to do is not be where some things are today with on-chip, say, 400 nanoseconds and off-chip 5,000 nanoseconds. That would limit our throughput to about 1,000, or our token rate for single user to about 1,000 tokens per second. We can get to 16,000 tokens per second if we can hit targets of on-chip communication of 50 nanoseconds and cross-chip communication of 200 nanoseconds. Most bar here is really speed of snail. The rightmost bar isn't speed of light. We're not propagating it at C or even C over 4, but it's a lot better, and we can ask, can we achieve that? So let's start by looking at the on-chip communication, right? So we basically do this dot product in one of these little SRAM arrays. We produce a single activation. That activation now needs to be moved to somewhere else on the chip to be the input activation for the next stage. One way to do this is to first of all, to complete the dot product by doing a reduction along adjacent PEs, and then to basically move this result. And we ought to be able to move it at wire speed. And on-chip wires have a delay of about a half a nanosecond per millimeter, 1 nanosecond per 2 millimeter delay. And so going from one end of the chip to the other end of the chip, in fact, one corner of the chip to the opposite corner, takes about 30 nanoseconds. And so if we introduce minimum delay in there, we can do this in 50 nanoseconds or possibly even less. But the key here is that we have to eliminate all of the unnecessary sources of delay. The unnecessary sources of delay are things like queuing. We can't have these activations sitting around in a queue waiting. We can statically schedule this communication. So when they show up at the wire, it's ready for them, they just go. And there's no time spent making a routing decision, no time spent on arbitration. It's simply, activations advancing over wires in a statically scheduled manner. And that can get us to 50 nanoseconds or less on-chip communication latency. And then we basically put the reduction into this network. So we may say, for example, if we're doing an 8K dot product, we may do 1K within the PE, and then we'll take 8 of those, and we'll basically do that dot product in the network to complete that reduction and distribute the results. So the next question is, what about off-chip communication? If you look at our off-chip communication today, it's very heavyweight. And the reason for that is we've spent a lot of effort over the years optimizing for throughput at the expense of latency. We wanted the highest per pin bandwidth to get to 400 gigabits per second per pair. And to do that, we had to do a couple things. One is we had to do heroic digital signal processing to basically pull a very noisy signal off the wires and detect a bit out of that. And that takes order of 100 nanoseconds. And then because there was still a residual error rate after doing that, we had to do forward error correction, basically having a powerful error correcting code that we would decode to find out what the real bit is, not the noisy bit that we detected. We can basically back off that trade-off a little bit by saying that if we're doing decode inference, where we're really worried about interactivity, we're much more worried about latency than we are throughput. And by backing off a little bit on throughput, maybe from 400 gigabits per second per pair to 200, we can now make the detection simple. We don't need heroic DSP. We don't need forward error correction. And so it's really just a serialization latency now. We simply sample in a receiver that bit, and then we have to sample a bunch of adjacent bits and deserialize them into a word at the lower bit rate to feed into our on-chip network. And we believe that this can be done in order of a few tens of nanoseconds, so you can get a complete traversal of a switch in something on the order of 100 nanoseconds. And to give you sort of a proof of existence, back in 2006, exactly 20 years ago, I worked with the people at NVIDIA Research. We built a machine called Black Widow. It had one of the first high-radix routers in it, a chip we called YARC. YARC had a fall-through time of less than 50 nanoseconds from input to output, with much slower technology than what we're working on today. So it's possible to build very low latency switches. And then another part of this is reductions. And part of these network operations, we're needing to exchange weights and sum them. And we can basically do this within network reductions and again, reduce the need for round trips. Another thing, if I look at the other end of the spectrum, where we want to get absolutely lowest energy per token for throughput limited cases. We're not as worried about interactivity. We basically want to minimize the data movement. Remember, that's where all of it is going today. And so the best way to do this is to basically use the spatial pipeline so we can keep on each chip the part of the KV cache needed for the user that we're doing currently. We'll route to different chips for different users. But we need to basically balance where we store this KV cache and where we store the weights for that matter with a memory technology that balances capacity and bandwidth. We need a lot of bandwidth to meet the demands of latency. We need a lot of capacity so that we're not having to spill to a distant memory where we then spend a lot of energy doing data movement to get it where it is. And while this isn't a technology that's feasible today, the thing we're very excited about is being able to store DRAM directly on top of the GPU chip, and to do it in a localized way so that the data we need for each of these little PEs is stored directly above it. And this basically eliminates the data movement energy. We get much better energy per bit, much better bandwidth, and we wind up with adequate capacity for the KV cache. It's not as much capacity as we'd get out of HBM, but we don't need that much capacity if we partition the problem correctly. Oops, what happened there? Okay. Okay. So if we put it together, what is the speed of light for fast decode? So to reduce the joule per output token, we want novel memory technology so we can put DRAM directly on top of the die, and then have SRAM distributed around the die with the arithmetic units placed right next to it. And this basically eliminates most of the data movement energy. We wind up with the joule per output token you reduced by 10x. And basically you're gonna get 10 times as many tokens per watt, 10 times as many tokens per dollar. And then to improve interactivity, it's really all about communication. And so we want to optimize for latency, sometimes at the expense of throughput. On chip, we simply want to basically eliminate all of the unnecessary sources of latency, queuing, routing, arbitration, clock domain crossings, get rid of those, and our latency is now just time of flight of the activations over the wires. Off chip, we need to build PHYs where we back off a little bit on throughput and get the latency down to just serialization latency for the PHY. And this can improve our interactivity by about an order of magnitude. And so these are things we're prototyping in NVIDIA Research, and we hope to be able to sort of sell them to the product groups, and you'll see them in future GPUs. Let me move on now to what I consider another important problem facing us in hardware for AI, and actually just AI in general, and this is running out of data. So a number of years ago, there was a great paper published that introduced the chinchilla scaling laws. Before that point in time, people would tend to try to get better accuracy by building really big models, but without increasing the data set so much. And what this paper really showed is that there was an optimum ratio of parameters in your model to tokens of data that you trained on. That was about 20 tokens per parameter. That's a blue line on this chart. And if you had more GPU flops, those are the horizontal or the diagonal lines going in the other direction, you wanted to stay on this blue line as you used more flops. And a bunch of popular models are sort of shown out there. But when we got to a certain point, roughly maybe 20 or 30 trillion tokens, we had mined out all of the easy data. Everything on the web had been scraped. All of the images that we had that we could feed into a OCR to pull data off of PDFs and JPEGs had been scraped. And now data was getting expensive. The only way to get data was basically to pay people to generate more data or to try to synthetically generate data, but there's some issues with that. So the real question is, in this data limited domain where we can no longer scale the amount of data we have by orders of magnitude every few years, what do we do to make our models better? And the tempting thing here is to think about how people trained AIs to play games. They started out training them on data with imitation learning, having chess programs or chess AIs look at grandmasters and see how they played, and having the Go programs imitate master Go players. But ultimately, they beat human capability by self-play, by having the AI play with itself. We'd like to do the same thing for large language models. And so rather than using more tokens, how do we get more value per token? And so the way we do conventional LLM training these days is we start with pre-training. We basically take all of these tokens we've accumulated, all this language data that's on the web, and we feed it into our large language model, and we ask it, what is the next token? We've given it all the words up to the next word. What is the next word? And it predicts the next word. If it gets it right, it gets a cookie. If it gets it bad, it gets an electric shock. After a while, it starts to learn to get it right. Then after we do that, we move into another phase. We do supervised fine-tuning, where we basically, on a much more curated data set, we try to get it to behave more the way we like, and then we move into a reinforcement learning phase, either with human feedback or with verifiable rewards, where we use reinforcement learning to further fine-tune. And this is where exploration goes on, where we're not relying on data, either the curated data for supervised fine-tuning or the bulk data for the pre-training. We're actually having the model explore. We're having it do some reasoning and then giving it a reward or not based on the result of that reasoning. But the question is, could we move this reinforcement learning phase earlier in this process and have it take place during the pre-training? And so, for example, if you do vanilla pre-training and the text up to the present is the line shown here, photosynthesis is a process plants, algae, and some bacteria use to make their own food using blank, right? If we just did it the normal way, it would either come up with sunlight or it would say, water or something, and we get the electric shock. If we do RLP pre-training, what we do is we tell the model, don't answer right away, think about it. So it thinks, okay, so photosynthesis relies on solar energy, hence the next token must be sunlight. And then it comes up with sunlight. And by doing this thinking, it's doing some exploration on its own. It's doing self-play in some sense. It's exploring the world as it knows it and will be rewarded or punished for that. And so the way RLP works is we have the same pre-training loop that we normally had, but now we run this policy and it gives us some exploration, and we wind up with two possibilities. We wind up with the result without any thought, that's a gray bar here, or the result with thought. And our reward then is this information gain, where we have to bias it based on priors, how much information was gained by coming up with the right answer where the normal model came up with the wrong answer. It has a little bit to do with how hard an answer that was. And by rewarding it in this way, we wind up improving the model considerably, so that over time we wind up getting a better model. And then that feeds back and makes it better the next time. So how well does this work in practice? So here are some results for Qwen 3, Nematron 2, and Nematron 3. And in all of these cases, it's improved the result by a significant factor. For Qwen, it's going from roughly 31% to 36%. For Nematron 2, it's almost a 20% improvement. For Nematron 3, it's about a 4% improvement. And one thing that is encouraging about this is that's after pre-training. Then the question is, after we then go through the supervised fine-tuning and reinforcement learning stages where we make the model stronger, does that wash the improvement out? And the answer is no, actually. So for Qwen 3, we had an 8% improvement at the base level. And then after all of the post-trainings, the supervised fine-tuning and reinforcement learning, we still have a 7% improvement. And for Nematron Nano, again, it's not washing out. We still wind up with very, very good improvements after the post-training, where the margin is maintained. So why does this work? So if we do some ablation studies on this, what we find is that the reason it works is we basically come up with a way to get the model to think for itself, basically to do this self-play by experimenting around. And then we also have gotten a way of giving it dense rewards. One of the problems with a lot of reinforcement learning approaches is you'll do a lot of work and a lot of work and a lot of work, and only at the very end are you going to get a reward. And so it's a sparse reward. Here we get a reward on every token. It's either you've improved, you got a differential information improvement, or you haven't. And so you're getting a lot of feedback that's adjusting the weights. And then it's very efficient. So if we start out with a 20 trillion token base on Nematron 12B, and we do this reinforcement learning pre-training on only 250 million tokens, we get a 35% improvement. So it doesn't take very much of this to actually make a big difference in the accuracy of the model. So reasoning can be used in pre-training. This is verifier-free because we know what the answer is. The gains are durable, they don't wash out during the fine-tuning stages, and it's very efficient to do this at scale. So let me move into the third little vignette here, which is about Groot. Groot is our robotics foundation model, and our vision is that we should be able to train one foundation model that will handle a lot of different robots, from bimanual operators, just a pair of arms or even a single arm, to bimanual operators on a mobile base, to full humanoid robots. And we should be able to train one set of skills that's generalizable, can handle any task, and not have to sort of have different policy networks for different sets of skills. And so the stack we have here is sort of on the left side, the hardware we want to target, from humanoids at the top to mobile bimanual robots at the bottom, to simple arms in the middle, simple arms at the bottom. The middle part of the stack is sort of what is going on in our actual robot foundation model. So we start with Cosmos Reason, which is our world model, and it's going to reason about the world, produce sort of scenes going forward of what we think is going to happen. This feeds into Groot VLA, which is a vision language action model. It will take a prompt asking it to carry out some task. It will have its inputs from the real world, cameras and other sensors, all the joint positions, so it knows the current state of the robot. And then it will command an action, which actually, depending on which robot it is a set of joint commands, move to this joint. And then to carry out that action, we have a whole body control model that basically operates in a much finer grain, where if you have an action that says move your arm here, it actually controls the individual joint movements to do that motion. On the right side of this graph, we show how we're dealing with the really hard problem with all of this, which is data. One of the reasons why LLMs have been so successful is we did have 20 trillion tokens on the web that we could kind of just scrape, and with a little bit of cleaning and the like, we could get good results out of them. That's not true for robot models. And so we spend a lot of time in our Groot lab doing teleoperation, because that was sort of the main way we had to collect data, but it's a very expensive and labor-intensive way to collect data. Every bit of data you got, some human had to control that robot, pick up the apple and put it in the bin, and that was relatively few tokens you got out of a lot of human time compared to generating word tokens where the humans just have to type. So what we do here is we have a synthetic data pipeline where on the top part, to train the VLA, we start with Cosmos Predict, another variant of our world model, where it will basically predict the future going forward from a certain point and generate a realistic video of that. We then feed that into Groot Dreams. And Groot Dreams is, in many ways, the opposite of the VLA. The VLA takes, sort of in a world model, basically pictures of the world and intent, and it produces robot actuations. Groot Dreams runs backwards, right? It basically takes robot actuations and it predicts what the world will look like going forward. And this allows us to generate, from the Cosmos Predict data, robot-centric data that we can then use to train Groot VLA. And then on the bottom level, the whole body control we train in Isaac Labs. So we basically take the robot, we put it into a simulated environment, and we use that to train the control systems to get very accurate. And then we have a bunch of mitigations to deal with the sim to real transfer when we come out of that simulated world, to make sure that those skills transfer to the real world. So the first part of this is Groot Dreams Dojo. And so the way we trained this model, which, remember, it's the action model backwards. It's basically, figuring out from, let's think of a robot simulator, figuring out from actuations what the output will look like, is we trained it on 44,000 hours of human videos. But the thing that was missing from these videos is what the action was. So we had to do a little bit of labeling to say what the latent action in this video is. So with the latent action and the videos, Dream Dojo then transfers these actions and can predict, what the world looks like going forward. It's essentially simulating, what the robot would do and turning that into video of what the robot would see. And the robot actions here now, along with the small-scale robot data set, give this now not with the humans doing the actions, but with the robots doing the actions, and it's generalizable to different types of robots, different types of objects, and different types of scenes. And so that data set has been very successful. The 44,000 hour video data set's been very, very successful in bootstrapping what is now a robot data set that would have taken enormous amount of time to generate with teleoperation. Now, one of the problems we had, and this is, I think, a classic problem with lots of AI applications, especially real-time ones, is that our original Dream Dojo model was too slow. Now, for robots, it's not as bad as self-driving cars. The self-driving car has to respond in a certain amount of time, or something bad will happen. It will have a collision or hit another car. With the robot, you can just make the robot go real slow, but that's not acceptable to us. And the original Dream Dojo was too slow. So we basically used the process of distillation to distill Dream Dojo down to a student, which instead of being slower than real time, in the case of Dream Dojo, is now 3 times faster than real time. So we have some time left on the GPU to do a few other things. And now we can take long action streams, feed them through the student, and in real time, get visualization of what the robot is doing. Okay, and these videos then feed a number of different things. They feed into our policy networks, they feed into the control, and they feed into a reinforcement learning process to make the whole thing better. So here's an example of Dream Dojo. First starting out with a unitary humanoid robot. You see the two hands there swiping the table. Then we'll flip to a unitary G1. This is a bimanual on a base. Again, carrying out a task. The same model, we'll flip it around, and now it's just with a simple bimanual model, putting the pillow down. And the final thing is a bimanual YAM. And again, this is trained from human video and then conditioned over to generate the robot videos. So now that we have Dream Dojo, which remember the whole purpose of Dream Dojo is to generate data to train Groot VLA, we can now basically train Groot VLA where we have, again, human video data, in this case 20,000 hours, and then we have a much smaller amount of in-lab human video where we have humans carrying out particular things and teleoperating robots that fine-tune the model. And the result of that then is a model that basically can handle lots of different types of actuators. And the way to think about this is we start out with the idea of, here's a VLA model, what do we want to have happen? Okay, we want to have the wrist do certain things, and then we want to have the individual hand joints do certain things. And then depending on which robot we're controlling, there'll be even more specific tokens that are sent to control that. Now the output of Groot VLA, I should have said this, and when you look at sort of the accuracy you get, it shows the importance of having more data. So this basically shows different amounts of training steps on the bottom, but the different lines are how much data you have. And so if you have 20,000 hours of human data, we're actually still improving even after 100,000 training steps. Whereas if you only had 1,000 hours of human data, you turn around at about 20,000 training steps. And so if we really want to improve this loss function to get our robots to be more accurate, data is the answer. And then this is an example of how Groot VLA rolls out. It's a relatively hard task, assembling some bolts. So it puts this piece in, it puts the bolt in, it grabs the screwdriver, and runs the thing home. And this is all done, a dexterous task, learned from doing video, and then by looking at the video, it's carrying out the task. Again, using the syringe to pull fluid from one to another, handling cards, folding a t-shirt. All of these things are done one shot, after training the model. Okay. So, the Groot VLA is giving sort of high-level commands. Those high-level commands need to be sort of decoded down into lower-level commands. And this is done through the Groot whole body control. And this is trained from 100 million motion frames and 500,000 parallel robot simulations in Isaac Lab. So it's basically trained in simulation. And so we'll have somebody generating commands, whether it's with a teleoperation or from video. We'll encode that motion, we'll have it carry out the action, and then basically seeing what the action does, we'll reward it. Again, it gets a cookie or it gets a shock, we'll adjust the weights, and we'll iterate over this millions of times, and actually millions of times with many variations on the model that's being used to try to make it more robust when we move to the real world. And we wind up with a very good whole body control model. So here's an example of the whole body control model going. I have to click it again to run the video, yeah. So it's able to pick up the cup, walk around, throw it in the trash. And this basically was sim to real from Isaac Lab without any fine tuning in the real world. Yeah, get the peanut butter. Robots, I guess, like peanut butter sandwiches. So I'm going to cut this one a little short just because I'm running out of time. Let me wrap it up. I have like 2 minutes left for questions. So NVIDIA Research is a really fun place. We try to run it very much like a university, but with the exception that we insist that the work that the researchers do be relevant to the company. If they're wildly successful, it should have a huge positive impact on NVIDIA. But in the meantime, we have a great playground. We can do really cool science. Today I've shared 3 things with you. Actually, I had to cut out the ML design hardware one. I forgot to take it out of the conclusion slide. Efficient inference. And so we can make super low latency interconnect that can get us to 10,000 or 20,000 tokens per second per user interactivity rates simply by optimizing for the right things in the interconnection network. And then to optimize for tokens per second per watt on the left side of the chart. We can build very efficient memory systems, DRAM stacked on top of the math chip, and then SRAM with near memory communication. The math unit's right at the sense amps of the memory, and that will basically minimize the data movement, which is where we're wasting energy in a lot of systems today. I'll skip over the one I didn't talk about. RL pretraining is really cool to overcome the data shortage because it gets us to the point of having our LLMs get smarter just by thinking, by carrying out thought experiments, not by being fed more data. And that thought experiment in this case is reasoning about what the next token is in that prediction, and that's great because it's a dense reward and it's a verifiable reward. You don't need to annotate what the correct answer is. You know what the correct answer is. And then I spent a little while showing you Groot robot models, which I think are really cool. And I think there's a whole bunch of Groot talks here at GTC. I encourage you to go see them because what Jim Fan and his team have done there is truly amazing. In this case, I think what's most amazing is getting around the robot data bottleneck by learning from very large quantities of human videos and then fine tuning on the robot specific data. And so there are literally hundreds of projects like this in NVIDIA Research each year at GTC. When I have to pick 3 or 4 of them, it's a very hard task, and so it's a really fun place to be. So with 1 minute and 12 seconds left, I will be happy to take any questions you have.
All right, one question. We literally have time for one question.
Hi. How large is your organization, and are LLMs being used to help you predict what research you're supposed to do next?
So the organization's about 500 people, and we use LLMs very extensively in our research, and it's across the board. They help us in coding, in writing RTL for hardware. We've actually built agentic systems to do exploration, where they'll basically suggest a line of research, carry out a bunch of experiments, and then reject that line of research and suggest another one. So we're trying to make AI be a partner with us in the research process.